Okay, biological monosaccharides. Glucose has come up a lot already this evening because it's the most important sugar in the human body. It's found in many, many foods. It has other names besides glucose, like dextrose and blood sugar, and its concentration in our blood is regulated by insulin and glucagon. I worked with a gentleman up in Boulder when I first moved to the United States, and sometimes we would go to a restaurant called Five Guys Burgers and Fries at lunch, and he would have to turn up his insulin, right, because he needed that to be able to deal with that large influx or that bolus of sugar that he was taking in eating there. Anyhow, under physiological conditions, glucose exists in a cyclic hemiacetal, and hopefully you remember what a hemiacetal is. A hemiacetal is when we have a carbon that has an ether group and a hydroxyl group attached to it. That's called a hemiacetal, where the C5 hydroxyl of the glucose molecule reacts with the C1 carbonyl group. And then we can form two possible isomers, which are going to differ in the location of the hydroxyl on carbon 1. And we end up with an aldohexose that has this formula, C6H12O6. In fact, if you've studied biology before, I'm sure you've seen this before as the formula for glucose. Now, keep in mind that you can have many aldohexoses with this formula, but it just so happens to be the formula for glucose as well. Here's how glucose cyclizes. If we start by examining the numbering of the carbons, we have the carbonyl. Right? This is our carbonyl, and carbon number 1, and carbon 2, 3, 4, 5, and 6. What it said on the last slide is that the hydroxyl from carbon number 5 is going to react with the carbon on the carbonyl. So that's carbon number 1. And so we form a bond between this oxygen and that carbon right there. Okay? In fact, I could draw a prettier curved arrow than that. We could say attacks that carbon like this. Now you might be thinking, well, come on, that hydroxyl is pretty far away from that carbon. But in fact, it's not, because the molecule has this kind of conformation or this kind of shape that's shown right here that actually gets this hydroxyl. This is the same hydroxyl here as it was here. It actually gets it pretty close to the carbonyl carbon. And so it can form the bond like this. Now, this curved red line that I have drawn represents the formation of a bond. But carbon, this carbon cannot have 5 bonds. It's already got 4. So that means you're going to end up breaking the pi bond. And when you break the pi bond, that oxygen is going to end up taking this hydrogen over here. Now, there's two possibilities. This hydroxyl can react with the carbon, and it can either attack it, and that's the correct word, it can either attack it from above, like this, and that's going to force the hydroxyl to point down like this, or it can attack it from below like this, and that's going to force the hydroxyl to be up. When that hydroxyl on carbon number 1 is down or up, okay, we have different names for them. If it's pointing down, we call that the alpha isomer or anomer, and when it's pointing up, we call that the beta isomer or the beta anomer. A way that my students taught me to remember this is alpha kind of looks like a fish, and fish live under the ocean, so which is down, and then beta kind of looks like a butterfly, and butterflies live up in the air, and so it's pointing up. So we have down for alpha and up for beta, like that. So again, glucose can exist as an open chain form. This is the open, what we call the open chain form. And it can also exist as a cyclic form. Now, what this slide is covering is how do we draw the cyclic form, which is a hemiacetal, starting with the open chain form. The first thing that we do is we're going to rotate the molecule. The way that I describe this rotation, it's like chopping a tree down, right? If you imagine that you have a tree like this, if this is, you take your axe, right? There's your axe, and you chop, 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 right? And then the timber falls in this direction. Well, if it falls in that direction, then all of the groups that are on this side of the molecule are going to hit the ground, right? They're all going to be down here. And so you can see that we have our aldehyde. On carbon number 2, the hydroxyl is going to be pointing down. On carbon 3, this hydrogen is going to be pointing down. Carbon 3, the hydroxyl is down. And on carbon 5, the last chiral carbon, the hydroxyl is pointing down. Then you have CH2OH, and that carbon isn't chiral. Then what you do is you twist the ring. You actually bend it like this. And it's always bent in the same way. The way that I usually teach my students is you always start by drawing this. You draw a 6-membered ring, and you leave out the top right bond. Just leave it out completely. Then you write in the aldehyde, CHO, like this. You put in a hydroxyl here, like this. And then you always put this up here, CH2OH. Okay? This is common to every monosaccharide that you're going to have to draw the chain form. Okay? You're always going to have this, and it's always going to be numbered in the same way. 1, 2, 3, 4, 5, 6. So then what you need to do is to decide which direction are the groups pointing on carbons 2, 3, and 4. When we cyclize the molecule and we make a 6-membered ring, we call that the cyclic form of glucose. And these rings, the way that they're drawn here, these are called Haworth, or sometimes pronounced Haworth projections. You can see that the lines are more wedged here at the front, and that's to show that the molecule is tilted towards you. The atoms in the front are tilted towards you, and then the atoms in the back are tilted away from you. Carbon number 1 in the carbohydrate, okay, this is carbon 1, this is carbon 1, C1, and this is C1. C1 is called the anomeric carbon. If the hydroxyl on the carbon 1 is pointing down, we call that the alpha anomer. And if the carbon at that, or sorry, the hydroxyl at carbon 1 is pointing up, we call that the beta anomer. So let's get back to that twist form that we looked at earlier, and that was this one here. If we go back here and we look at carbons 2, 3, and 4, on carbon 2, you can see that the hydroxyl is pointing down. So that means the hydroxyl will be pointing down like this. On carbon 3, the hydrogen is pointing down. And on carbon 4, the hydroxyl is pointing down. Now we just fill in those carbons with hydrogens or hydroxyls. On carbon 2, the hydroxyl is down, so it's a hydrogen up. On carbon 3, the hydrogen is up, so they're down, so it's a hydroxyl up. And on carbon 4, the hydroxyl is down, so the hydrogen's up. Then all we have to do is make our bond between this oxygen and this carbon. Maybe I should put it in a different color. We do like this, okay? Like that. We make our new bond. And then depending on whether we want to draw the alpha or the beta, or the alpha or the beta anomer, we'll have the hydroxyl pointing up or down. If we want to draw the alpha anomer, the hydroxyl is pointing down. And if we want to draw the beta anomer, the hydroxyl is going to be pointing up. In fact, if you have glucose in solution, it actually exists in an equilibrium, which is called a mutarotation, where we have 37% of the alpha anomer and 63% of the beta anomer. This is a step-by-step procedure for drawing a Haworth projection from the open chain form, which is another way of saying an acyclic sugar. And here we're dealing with an aldohexose. The molecule is called D-mannose. So this isn't D-glucose, but we're going to go over how we would go about drawing the Haworth projection or the Haworth projection of this molecule. Well, remember that the first thing we're going to want to do is we're going to tilt this molecule or rotate it so that it's on its side. We're going to have to knock it over, so to speak. But there's an even easier way to do that. And let me show you what it is. The easier way is to just always start by drawing this. You have a 6-membered ring. It has an oxygen in the top right corner. And then you have the CH2OH on top of the ring at this carbon right here. Okay? That is the easiest way to do it. If you can remember how to do that, then you can always draw the halo projection correctly. Let me show you why. Because if you number the carbons, 1, 2, 3, 4, 5, 6, you start here on the anomeric carbon, 1, 2, 3, 4, 5, and 6, like this. Well, if I want to figure out which direction the hydrogens and the hydroxyls are pointing on carbons 2, 3, and 4, on carbon 2, 3, and 4, whatever is on the right-hand side is going to be pointing down, and whatever is on the left-hand side is going to be pointing up, like that. So that means on carbon 2, we have a hydrogen pointing down, hydroxyls up. Carbon 3, we have a hydrogen down, hydroxyl up. And on carbon 4, we have our hydroxyl down and our hydrogen up. Now you might be wondering, hey, Mr. Dion, you left out, the first carbon. Well, that depends on whether we want to draw the alpha or the beta anomer. If I want to draw the beta anomer, I'm going to draw the hydroxyl pointing up like this, proton going down. This would be beta E nanos. If I want to draw the alpha anomer, delete that. I would put the hydroxyl going down, the hydrogen going up, and then this would be alpha D nanos. Again, the anomeric carbon, we have to decide whether we want to draw the alpha or the beta anomer, and that governs whether the hydroxyl is pointing up or down. We add in our hydroxyls. Again, I told you that everything on this side is pointing down, 2 hydrogens in the hydroxyl. Everything on this side, the left-hand side, is pointing up, 2 hydroxyls in this hydrogen. And again, then we just make a call as to whether we want to draw the alpha or the beta anomer. Fructose has other common names like levulose or fruit sugar. It's found in things like fruits, apples, strawberries, and the like. Corn syrup, it's found in honey. It's, in fact, the sweetest sugar, and it is a ketohexose. It's wise for you to know that it is a ketohexose, and you can clearly see that it has a ketone, and it is a hexose because it has a total of 6 carbons. You do not have to know how to draw the cyclic form of alpha and beta D fructose. I'll never ask you to do that. Galactose is the principal sugar that's found in mammalian milk. It's an aldohexose that is very close in structure to D-glucose. Where it differs from D-glucose is in the chirality at this carbon right here. In D-glucose, it's just reversed. The hydroxyl's on this side, and the hydrogen is on the other side. D-galactosamine is a component of the blood group antigens. Again, you can see that galactose can cyclize to give you either alpha D-galactose or beta D-galactose. If I asked you to draw that, you would start by drawing the 6-membered ring with the oxygen in the top right corner, your CH2OH up here, hydrogen pointing down. Let's say we wanted to draw alpha D-galactose. We put our hydroxyl pointing down like this, and then carbons 2, 3, and 4. We have a hydroxyl pointing down, a hydrogen pointing down, and a hydrogen, a hydrogen pointing down, and then we just fill these in with the opposite, with this, And there you go. And you can see that what I have drawn here is identical to alpha-D-galactose. Again, glucose and galactose only differ in the orientation of one hydroxyl group. It's the hydroxyl group at carbon 1, 2, 3, carbon 4. That's what I showed you before. Carbons 1, 2, 3, and 4. It's on the fourth carbon is where they differ. Ribose and deoxyribose are 5-carbon sugars. They're obviously important. They're found in DNA and RNA, and they exist mainly in a cyclic form. They are aldopentoses. The only difference between the two is that obviously deoxyribose, you can tell from the name, is missing one oxygen. We have a hydroxyl here, and we simply have a proton here in deoxyribose. Benedict's reagent is a reagent that can be used to identify sugars. The aldehyde group of an aldose is going to be oxidized by this reagent. It's called the Benedict's reagent. The Benedict's reagent is nothing more than an alkaline or a basic solution of copper 2+ ions. Copper 2+ is a beautiful blue, deep blue color, kind of like aqua velva or Windex or something. What happens is when that copper 2 is in the presence of an aldehyde, it gets reduced to copper 1. And copper 1 is red. The conclusion then is that if you have an aldose, you can detect it by the color change, because when it reacts with the blue copper 2+ ions, it reduces them to copper 1 ions, and we make a carboxylate, and it goes from being blue to red. So this test was historically used to quantify the amount of glucose in the urine of diabetic patients many years ago, before faster and more accurate tests were devised. A reducing sugar, in fact, is any monosaccharide except any monosaccharide and disaccharide except sucrose. So sucrose is a disaccharide. All the monosaccharides that we look at, and all disaccharides, with the exception of sucrose, are reducing sugars. If you're wondering, what the heck is a reducing sugar? Well, if we go back here, what's happening? We can't have oxidation without reduction. It's impossible in chemistry. So as this is being oxidized, right? Oxidized, what's happening to our copper? It's being reduced. And so a monosaccharide is a reducing sugar because it's reducing copper 2+ to copper 1+. Now you might wonder, could a ketose be a reducer, or how could a ketose be a reducing sugar because it doesn't have an aldehyde on it? Well, a ketose, like fructose, can isomerize to give you an aldose via an ene diol. And this is an ene diol. This is a new functional group you should be able to recognize. It's an ene from an alkene, and it's a diol because there's two hydroxyls, a diol, so an ene diol. So you should be aware that a ketose can rearrange or isomerize to an ene diol, which isomerizes again, give you an aldose, and it will be a reducing sugar. So that's why fructose is a reducing sugar. Let's look at some biologically important disaccharides. The anomeric hydroxyl of one sugar can react with a hydroxyl on an alcohol or sugar to form a glycosidic bond, and water gets lost to form an acetal. Here's the anomeric carbon, if D-glucose reacts with another molecule of D-glucose, this hydroxyl can react with the hydroxyl on carbon 4 of another glucose. We can lose a water molecule and we form this new bond. And that bond is an acetal. Remember that an acetal is when we had a carbon that had two ether bonds to it, like this. Here's the carbon. This is the carbon in the acetal. Look, you can clearly see that it has an OR group attached to it here and another OR group attached to it there. So maltose, the disaccharide that's formed from two glucose molecules, is an acetal. Now we describe this glycosidic bond using alpha 1,4. What does the alpha refer to? The alpha does not refer to this carbon here. The linkage between the two sugars is alpha 1,4 because the bond here is going down, right? And if it's pointing down, it's alpha. It's also between carbons 1 and 4, and that's where alpha 1,4 comes from. The reason that this molecule is beta maltose, the beta comes from this carbon over here that the hydroxyl is pointing up. So we could have beta maltose and we can have alpha maltose, but the glycosidic bond would not change in neither alpha or beta maltose. They would be the same. What would change in alpha or beta maltose would be the orientation of this hydroxyl on the far right. So the glycosidic linkage that joins two rings can be either alpha or beta. If it's pointing down from carbon 1 on the sugar on the left, it's an alpha linkage, and if it's pointing up, then it's a beta linkage. Maltose is formed by linking two D-glucose molecules together in that alpha 1,4 glycosidic linkage. We call maltose malt sugar sometimes. It's an intermediate that's formed in starch hydrolysis. It's also a reducing sugar. Remember that in order to be a reducing sugar, you have to have a hemiacetal or an aldose or a ketose. Well, remember that a hemiacetal looks like this. You have a carbon with a hydroxyl and an ether on it. If I look at this carbon, you can see it's got a hydroxyl attached to it and it has an ether attached to it. So since this disaccharide is a hemiacetal, it is a reducing sugar. It's going to reduce copper 2 to copper 1 from the Benedict's reagent, and we would see a color change going from blue to red. Next, we have lactose. Lactose is formed by joining beta D-galactose to D-glucose to give a beta 1,4 glycoside. Why is this a beta linkage? Because when I look at the bond formed between carbon 1 on the sugar on the left and carbon 4 on the sugar on the right, this hydroxyl is pointing up, right? That's beta. So we draw this bond pointing up. So it's beta 1 to 4. Okay? The fact that this is is called beta lactose has this B right here, that beta has nothing to do with this, nothing to do with that whatsoever. That beta has to do with this carbon over here and the fact that the hydroxyl is pointing up. Lactose, you probably know, is milk sugar. It's used as an energy source, but it's going to be hydrolyzed into glucose and galactose before it can be used. Lactose intolerance results from a lack of the enzyme lactase, and thus the inability for people to hydrolyze that glycosidic bond found in lactose. And so they're unable to metabolize it properly. In order for lactose to be used as an energy source, it's going to be converted to a phosphorylated glucose molecule. And when you don't have the enzymes necessary to convert it, you get a genetic disease called galactosemia. which can lead to many different problems. People who lack the enzyme lactase are around 20% of the population. Sucrose is formed by linking alpha D glucose with beta D fructose to give a 1,2 glycosidic linkage. Remember, you have to be aware of the fact that sucrose is not a reducing sugar. It does not possess a hemiacetal. The glycosidic oxygen, in fact, is part of an acetal. Sucrose is an important plant carbohydrate. It's obviously found in things like sugarcane, and it's water soluble. It's very easily transported in the plant circulatory system and cannot be synthesized by animals. We have several different words or names that we use for sucrose. One of the most common would be table sugar. So when you go to the store and you buy sugar, that's table sugar, is sucrose. Cane sugar, beet sugar, and of course, unfortunately, it's linked to cavities. Here's the glycosidic bond formed in sucrose. We have our alpha glucose and our beta fructose molecule, and then when we link them, we get what's called an alpha 1 beta 2 linkage. Where does that name come from? The sugar on the top, the glucose molecule, this oxygen is pointing down, so this is alpha, and it's on carbon 1, so that's alpha 1. And then from the fructose portion of the molecule, the glycosidic bond is going up, so it's beta, and it's on carbon 2, so we have beta 2. So we call this an alpha 1 beta 2 linkage. If you examine the structure of sucrose carefully, you'll see that there are no hemiacetals in sucrose, and thus it is not a reducing sugar. Polysaccharides. So starches are storage forms of glucose that are found in plants. They are polymers of alpha-linked glucose, all linked together. If the links are only 1,4 links, then we end up with a linear polymer of glucose, and we call that amylose. And when you tally up or put together all the 1,4 linkages, that linear amylose starts to assume a helical configuration that has about 6 glucose units per turn. But amylose, as a matter of fact, only makes up about 20% of plant starch. The other 80% is made up of amylopectin. And so when we have a mixture of both alpha 1,4 linked glucose molecules with 1,6 linkages in them, then it gets branched, and we call that amylopectin. The branches in amylopectin are frequent and have lengths of approximately 20 to 25 glucose units. Here's the structure of amylose. We see the alpha 1,4 linkage of the glucose molecules, and then you can see how if you put enough of them together, you get this alpha helix where they turn, you get a right-handed turn like this, okay? And it says we have approximately 6 glucose molecules for every turn. You can see here, 1, 2, 3, 4, 5. It's kind of hard to see there, but you can see that it's close to 6. Now, remember, in amylopectin, we have branching. We still have that same old alpha 1,4 linked chain that we had in amylose, but we end up with these branches that are called alpha 1,6 branches. So they're off of these hydroxyls, right? You see the branch right here. And again, in amylopectin, the branches are frequent, and they're only about 20 to 25 glucose units long. Glycogen is the major glucose storage carbohydrate in animals. It's a highly branched polymer like amylopectin, but we have more frequent branches, and they're shorter, only about 10 glucose units long. Glycogen is stored in the liver and in muscle as well. Cellulose is the major structural polymer that's found in plants. It's a linear homopolymer composed of beta D glucose units that are beta 1,4 linked. So amylose was alpha 1,4 linked, and cellulose is beta 1,4 linked. And you can see there's a big difference there because we can digest starches, but just based off of going from an alpha to a beta linkage, we are unable to digest cellulose. The repeating disaccharide in cellulose is beta-cellobiose. The repeating disaccharide that's found in amylose is maltose, as we looked at earlier. In animals, lack enzymes necessary to hydrolyze cellulose. Even things like, or even animals like cows don't have the enzymes, but they possess bacteria which can digest the cellulose so that they can eat grasses. Here's the structure of cellulose. Again, we have all those glucose molecules. It's only the way that they're linked together that differs from amylose. Right? In amylose, we had an alpha 1,4 linkage, and now in cellulose, we have that beta 1,4 linkage. Here's a comparison of the glycogen and amylopectin structures. Again, you can see that they're essentially the same in that they both have alpha 1,4 chains, and they both have alpha 1,6 branches. But what did we say? That in glycogen, we had more frequent branches, and the branches are shorter. In amylopectin, we have longer branches, but they are less frequent.